The next thing that we're going to talk about is angular or rotational momentum. And to do that, before we get into the angular part, I want to go back over linear momentum. So, just as sort of a quick example of the kind of thing that we're going to compare this to. Linear momentum, we used a little p for, and linear momentum was just the mass of an object times its velocity. So, anytime an object moved, a straight line, had any kind of velocity at all, that object has momentum. We also said that that momentum was conserved. So the initial momentum was equal to the final momentum. So if two objects ran into each other, one object lost momentum, the other object gained momentum, and those exchanged momentum for the same amount. So that's our conservation of momentum. The initial momentum is equal to the final momentum. And that momentum is conserved as long as the net outside force is zero. All that means is that the object is free to slide. So as long as both objects are free to move around, we say there's no outside forces acting on the system, and the momentum is conserved. So as long as nothing is nailed down, essentially, we're going to say momentum is conserved. So for linear momentum, what we're looking for is objects being free to slide. So a quick example of that, let's say we have a 2 kilogram mass traveling at 5 meters per second towards a 6 kilogram mass going 3 meters per second, and those two things stick together. And we want their final velocity. What we're going to do is use the conservation of momentum to do that. Both of these objects are free to slide around, so we can say that momentum 1 plus momentum 2, the beginning, that's our total momentum for the system. That's how we find the total momentum for our system, equals the final momentum for our system. So let's just go ahead and plug that in. M1v1 plus M2v2 equals, now that they're sticking together, we have M1 plus M2 times final velocity. When these two objects stick together, when they're together at the end, the inertia of each object combines. So we take their two masses and add them together because they're moving together afterwards because they've stuck together. So we plug in our numbers. 2 times 5 plus 6 times 3 is equal to 2 times 6 times V final. 10 plus 18 is equal to 8 times V final. And we can solve for V final. That's 28 equals 8 V final divided by 8. And V final comes out to be 3.5 meters per second. That's how we do angular. That's how we do linear momentum. Initial momentum equals final momentum, and then we fill out each of those numbers. So in this, we see that total momentum is conserved. We have the same amount of momentum beforehand as we did afterwards. It's the only way we could solve this problem. Mass 1 slows down. So mass 1 loses momentum. Mass 1 has less momentum than when we started. Mass 2 speeds up. Goes from 3 meters per second to 3.5 meters per second. Mass 2 gains momentum. That's linear momentum. Angular momentum, it's kind of the same idea, but we're going in a circle. For angular momentum, it's an L. Don't ask me why. And instead of mass, we have rotational inertia, I, and instead of linear velocity, we have angular velocity, omega. So L is equal to I times omega. And just like Okay, so I is rotational inertia, and omega is angular velocity. So the difference here is that we're talking about those angular and rotational quantities. Instead of mass, rotational inertia. Instead of velocity, angular velocity. And we also have the conservation of angular momentum. Angular momentum will be conserved as long as the net outside torque on a system is zero. What that means is that as long as the objects are free to slide, as long as the objects are free to spin around, we have conservation of angular momentum. We can say that the angular momentum is the same before and after. So what we're looking for is free to spin, free to rotate for angular momentum. Now, another thing, and this may be one of the more difficult parts of this to understand, is that anytime we have an object moving in a straight line, it's going to have an angular momentum. But angular momentum is always in relation to a point. So objects moving in a straight line have angular momentum about any given point. So we're going to go through this because we're going to have straight line objects running into spinning objects. It's the best. When we're choosing this point, we're always going to make this point the rotation point or the pivot point for the system. And that should be a pretty obvious thing to find. So, when we're trying to do angular momentum, it always has to be in relationship to a point, and it's going to be most convenient to make that point the point of rotation for the system. So, let's say we have a mass moving with a velocity v, and that point is my pivot. I want to figure out his angular momentum. So, that line for the velocity is the line of action. Okay, the mass is going to travel along that line the whole time. What we're going to do is say that our line of action is a distance of a away from our pivot. It's the closest the line of action gets to the pivot. That's a very important distance, that a. That's the distance from the line of action, we use the LOA, to the pivot. And then the distance from the mass m to the pivot is r. Okay, that's very important. We can see that that velocity and that radius don't quite line up. But they're also not perpendicular to each other. So let's look at what's going on with this. I know angular momentum has to be the moment of inertia I times the angular velocity. Well, in this case, I just have a point mass moving. And the rotational inertia of a point mass moving is just mr squared. And omega for an object is v over r. Now, there's an important thing that we have to do with that v. So, moment of inertia is mr squared. Angular velocity is v over r. When we're talking about angular quantities, and you may have to remember all the way back to the first video, only the perpendicular part of the velocity, only the velocity that is perpendicular to the radius, contributes to angular velocity. The part of the velocity that points along the radius doesn't matter to me. So when we're converting from velocity to angular velocity, all we care about is the perpendicular part of the velocity. The perpendicular part of the velocity, in this case, for the angle that we have, is the velocity times the sine of theta. And as we can see, as that mass gets closer and closer to the pivot point, more and more of that velocity becomes perpendicular. So the angular velocity part kind of grows. So let's put that into our equation. Let's see what's going on. So L equals mvr sine theta over r. We can clean that up a little bit, eliminate one of the r's. So now we have L equals mvr sine of theta. Again, as we can see, as that mass moves, the radius gets smaller and theta gets bigger. Those two things change. But radius times sine of theta, that's the hypotenuse times the sine of that angle, always equals the opposite side, A. And that A part never, ever, ever changes. So, to simplify, anytime an object is moving in a straight line, its angular momentum is going to be m. Okay, A doesn't change, which is nice. So any object moving in a straight line has mva. And the really important part of this is that if the object has constant velocity, it's also going to have constant linear momentum, and it's going to have constant angular momentum. An object moving with constant velocity does not have a torque acting on it, so its angular momentum has to be the same. So an object with constant velocity has constant angular momentum. Constant L. Understanding the angular momentum of an object moving in a straight line, in my opinion, hardest part. You get this down, that the angular velocity of an object moving in a straight line is mva, we'll be good to go. So let's look at an example. A 20 kilogram little girl is running with a velocity of 10 meters per second, and she jumps onto the outer edge of a merry-go-round. She makes it spin around. Now, this merry-go-round, I'm just going to do MGR. This merry-go-round has a rotational inertia of 75 kilograms per meter squared, and that outer radius is 3 meters long. What I want to do is figure out how fast it's going after the girl jumps onto it. What's its final angular speed? That's going to tell me how fast that merry-go-round rotates around. So let's look at a quick picture. We've got a merry-go-round. There's our pivot point in the middle. There's our little girl running at 10 meters per second. Now, from this situation, we see that both objects are free to spin, which means we can use the conservation of angular momentum. That's going to and we know the conservation of angular momentum has an omega in it, which is very important for finding the final angular speed. So, initial angular momentum is equal to final angular momentum. In the beginning, so our possibilities for initial angular momentum are the angular momentum of the girl plus the angular momentum of the merry-go-round. If the merry-go-round's not moving, it doesn't have any angular momentum to begin with. The angular momentum of the girl, since she's moving in a straight line, is mva. If we look at her action and how she's going to jump onto the merry-go-round, A in this case comes out to be R. So we'll plug that in a second. But mva always, for angular momentum, plus 0 equals the final moment of inertia. We're going to talk about what happens there, plus omega. Alright, so the girl's angular momentum equals the final angular momentum of the system. mva equals I final angular momentum, final rotational inertia times omega. Alright, because the girl lands on the merry-go-round, the rotational inertias combine, they add together. So the final rotational inertia is the rotational inertia of the girl plus the rotational inertia of the merry-go-round. Now the girl is going to act like a point mass on the edge of the merry-go-round, so it's just going to be her mass times her distance from the pivot point squared, or mass of the girl times r squared plus 75, which is the moment of inertia of the merry-go-round. That's my final rotational inertia. So we're going to plug all of the things we now know into the equation and solve for that final angular velocity. So mvr equals that final rotational inertia times omega. Just plug our numbers in. Solve for everything. So we got 600, 180 plus 75 times omega. And we get our final angular speed. Divide by that. And it's 2.35 radians per second. All in all, I think that's pretty simple. So, we're not going to do this, but just kind of think through what would happen to that final angular speed, or final angular velocity, if the little girl were to jump not onto that outside edge, but a little bit closer to the middle. Basically what we're saying is, what happened if A were smaller? What if she ran and jumped like that instead of onto the outer edge? In this case, the merry-go-round would have less angular velocity afterwards because the girl had less angular momentum to begin with. That A is smaller now, so she has less angular momentum. So the system has less angular momentum. And we'll say it again. The girl has less initial angular momentum. So the system has, sorry about that. The system is going to have less final angular momentum. All right. Another interesting thing I like to talk about with angular momentum is kind of what happens to just a single object that's spinning around, like an ice skater or somebody spinning around on a chair. And we know that as they bring their arms in, they speed up, and as both of those things bring their arms out, they slow down. Arms in, speed up. Arms out, slow down. And the question is, why do they speed up as they move their arms in? What exactly is happening? So let's kind of look at what's going on with our system. The angular momentum of each of these things has got to be conserved. And there are two reasons for it. One, the line of action for that force pulling in is along the radius and is an internal force. These two things tell me that the net force acting on the system, the net torque acting on the system is zero. When there is zero net torque, angular momentum has got to be conserved. Okay. Those are internal forces and they're along the radius, so there's no torque. If that's the case, that number L isn't going to change. And as they bring their arms in, they're decreasing the radius, so they are decreasing their moment of inertia, and they are increasing their angular velocity. That's what's happening in that situation. When they pull their arms in, moment of inertia comes down, and the angular velocity goes up, because angular momentum is conserved.